So this was the discussion about these questions, and hopefully it sort of clarified some of your doubts. But today, sort of the rest of the time, let me actually sort of say more mathematically, what does this topologically equivalent mean, and what is a surface, and so on. Okay, how do topologists think about this, right? So when we do mathematics, we can't always draw pictures. Remember, the topological spaces might not just be surfaces that we can imagine. It might be higher dimensional things, and this came up last time also. So how do mathematicians write down sort of make these notions precise? Okay, so just remember, so recall what we had sort of informally, right? So what we said earlier, that informally was that topologically equivalent meant that so two surfaces are topologically equivalent if you can stretch or shear or bend them, deform them from one to another, stretch and bend without tearing them or gluing, right? So this is what was the sort of informal definition, right? So, but how does one make this precise? Okay, how do you make it precise is the question. Okay, so how do you how do you make it precise? Well, I have to start with a notion of continuity. Okay, so remember that this sort of, I want to say that you can deform one space to another continuously. Okay, and so I kind of, let me sort of recall something that I'm sure that most of you have seen. It's in your first year of calculus or something like that. So it's a notion of continuity. Okay, and there is a sort of a definition that you have seen. Let's say let's talk about maps from R to R. So you're mapping points in the real line to points in the real line, right? So when do we say that f from R to R is continuous? Well, if I remember this definition, that either, I mean, I'm sure you have come across it, and I mean, might seem intimidating when you first see it, but it's actually something that makes sense after a while. So this definition looks like this: if any x in R and any epsilon greater than 0, there exists delta greater than 0, such that if you have x minus y less than delta, then this implies that f of x minus f of y less than epsilon. Right, so there's a mouthful, right? And it takes sort of time to parse this. But what it really means is that here's my real line, and here's f mapping here. So I want to say it's continuous at x. So x maps to f of x. Continuous at x means that, if you take a small neighborhood of, this is an epsilon neighborhood of f of x. Okay, so this, maybe I should use another color here. So this open interval here, if I want to land, so if I fix such a neighborhood, then there's always going to be some small enough neighborhood of x that lands up in there. Okay, so this small enough neighborhood kind of fits in there. All right, so this is what was continuous means. So let me just say this: so you can choose a small, let's call it delta neighborhood here, so that f takes that delta neighborhood inside that red epsilon neighborhood, right? So this was, and no matter what epsilon neighborhood you choose, you can always do that. Okay, this was what continuous means, and I mean, sort of something. It's worth so trying to understand when something is not continuous, right? So, well, if you look at a function, let me draw the graph of a function that is obviously not continuous. So maybe it's from R to R, and so such a function might have a jump, right? So you all know. So this is the graph of x. So I'm drawing the graph of f. So this graph is, by the way, different from the graph we were talking about, right? So this is the graph in analysis. So I hope that it's not confusing. So this is a graph of x. So this is so x mapping to, let's say, f of x. So what happens? So as it approaches, so maybe I should put this as a dot here. So as it approaches x, it's sort of in this lower part here. And then suddenly at x, it takes the value f of x and it jumps up. Right? And you all know that this is discontinuous, right? Even when you're trying to draw the graph, you have to lift your pen up and jump it. And you can see that that this sort of definition fails. Okay, and it's sort of, I'm sure that you've seen this, so I'll leave that to you. But now let me give you an equivalent definition. All right, so it's an equivalent definition. So this definition involves the epsilon delta. I'm going to, so I don't like these epsilon deltas to keep track of all these quantifiers, logical quantifiers. But there's one very neat way of describing what continuous is. So I can say that FR to R is continuous if the pre-image of any open interval is an open interval. Okay, so or as a well, I should really say it's an open set. Okay, the open set is it's a union of open intervals. Okay. Okay, so so what does that mean? So here, so let's see whether this holds for this not continuous example. So what happens when you take this open interval? So remember this so when you draw a graph, this bottom line is this source R, and this vertical line, this y-axis is the target R, right? So this is the sort of the real line, that's the domain, and this is the range. And so when I'm talking about open pre-image of an open interval, I have to take an open interval in the range. So if I take an open interval around this f of x, right? So this guy here, what is its pre-image? So pre-image means all the points that map inside this interval, right? So when you take this pre-image, then what you would get on the domain R is something which is this is a semi-closed interval. It's something that looks like this, right? This point is included. This point X is included, right? It's no longer an open set. It's not an open interval, neither is it a union of open intervals. So you probably have seen this definition of open sets in R and Rn, if you've done a little bit of analysis. So, but what happens is that this green interval, that is the pre-image, is not an open interval, and it's a sort of closed and open on one end and closed on the other, right? It includes that point X. Okay, so so this is this definite, by this definition, if you believe this definition is equivalent to the the definition involving epsilon and delta, so this definition tells you that this is not a continuous function, which you already knew. Okay, so I leave you to check that this definition that I now gave is actually the same as the epsilon delta definition. Okay, you can sort of go back and forth. Something is continuous by that definition is also continuous by this, and so on. Okay, so it's actually an equivalent definition. All right. So and the good thing about this definition is that this definition of continuity, right? So this is the definition of continuous, is that this generalizes to other spaces, various other spaces. So this generalizes to other spaces. For example, whenever X is a metric space. So suppose you have a metric space. Metric space is something with a distance. Okay, this is something that you might have already seen in if you're reading topology, that sort of you have a space with a notion of a distance between them. So the space might be some set, maybe it's some region on the plane. It might be something abstractly a set, but the point is that whenever you take two points in that space X, there is a notion of a distance dxy, which is some positive number which measures, how far they are from one to another, right? And so this distance has to satisfy some properties, right? So if the distance is 0, then it better be the same point, and so on and so forth, right? So that's a metric space. And the good thing about a metric space, there is a notion of an open interval, right? An open interval is something like a neighborhood, right? It's of a point, okay? So here, what replaces the notion of an open interval is the notion is a disk or a ball around the point of containing. So there's a notion. So a metric space has a notion of an open neighborhood, just like an open interval is sort of a open neighborhood of a point. So the open neighborhood of a point, let's call it little x and capital X. And what is that open neighborhood? Well, for any delta, I can look at all the points in the space such that the distance of x and y is less than delta. Okay, so this is sort of the open neighborhood I'm talking about. So sort of fix a delta bigger than 0, and then you look at this. So this is like so if you look at in the picture here, then you will see that you get some kind of, some kind of, so you can imagine at higher dimensions, it will be a ball. And this is called a metric. So a metric ball of radius delta. Okay, and so these guys, they form notions, generalizations of an open interval. Okay, and then the same definition of continuity works between metric spaces. So let me write it down in sort of the definition. So if you have x and y are two metric spaces, they're sets with some notion of a distance between points. Okay, and then f from x to y is a continuous, is said to be continuous. So this is the definition of continuity of a map. Continuous if the pre-image of any metric ball, I should say it's an open metric ball, right? So it's all strictly less than delta. So any open metric ball is an open set. And this open set means it's a union of open metric balls. Okay, so this is what continuity, the definition of continuity, how it generalizes. And it generalizes not just to a metric space. You can define a topology on a set. Okay, so let me just remark it generalizes further. You can define a topological space. A topological space can be defined by taking a set X and saying which subsets are open. You can define your open subset. Of course, you have to have some properties, some sort of compatibility. Okay, so if you take a union of two open sets, it has to be open, and each point has to be contained in an open set. So under some axioms, if you can sort of define your notion of what opens are. So mathematics is great because it offers this kind of flexibility and sort of abstraction. So it abstracts out, what actually you need to sort of, it sort of discards the irrelevant stuff and gets to the core of whatever makes things work. And in this case, in the notion of continuity, what makes things work is this notion of neighborhood. Okay, so you're jumping into the neighborhood of another point and so on. So this notion of neighborhoods is abstractly sort of packaged in a notion of this collection of these open sets, and And this is, in turn, can be used to define what a topological space abstractly is. Okay, so there is a more abstract notion of a topological space, but for most practical purposes, this notion of topological space that's used for us is a metric space. Okay, where there is a notion of a neighborhood that comes from the metric. Okay, so so things near to you are things which have distance less than some epsilon that you choose or delta that you choose. Okay, so this is so let's stick with metric spaces for now. There's no harm done in sticking with metric spaces.